Okay, today we will continue on talking about the organic matter. If you remember last time in the last lecture, we talked about the functional groups. And today, most of the lecture will be about the ionization of these functional groups. An important characteristic of organic functional groups is the ability to ionize and form anionic or cationic species. To ionize to give you ions, so either anions or cations. The ionization occurs through proton dissociation or association reactions. So either they give you proton dissociation, the proton or hydrogen leaves the group, or it takes hydrogen. The ability of a functional group to donate protons to a solution is a characteristic of Lowry-Bronsted acidity. We are not going to talk much about this. You should have taken this in chemistry, but that's what they call these. Lowry-Bronsted basicity is the ability of a functional group to accept a proton from the solution or to donate a hydroxide. So basicity, so that we can call it a base. Remember, the acidity is donation of protons, giving a protons. Basicity is to accept a proton or hydrogen or to donate a hydroxide OH group. Lowry-Bronsted acids and bases are described by their strength and a parameter called the acid dissociation constant, Ka. That's what we will be talking about in detail today. All reactions that involve acceptance or the donation of a proton are uniquely characterized by a Ka value. We'll take an example, the dissociation of a carboxyl group, COOH, that's the carboxyl group, in methoxyacetic acid. So this is the undissociated methoxyacetic acid. If it dissociates, it gives you the negatively charged ion and releases a proton or hydrogen ion. At equilibrium, the distribution of the carboxyl functional group between the protonated and deprotonated forms is described by the acid dissociation constant, which we write just like any equilibrium constant. Remember, these organic acids are weak acids. That's why we talk about Ka. You don't talk about Ka or any K for strong acids like HCl, H2SO4, HNO3. They are totally dissociated. They completely dissociate, 100%. So we do not have to talk about their Ka or their dissociation into two entities, hydrogen and a negatively charged ion. So Ka, just like any reaction, you multiply hydrogen by this, okay, divided by this. Now, if you remember in the simple inorganic chemistry, we have seen that molecules, if they are pure molecules or pure liquids, we give them the value of 1, the activity of 1. Not in these weak acids and bases, we cannot do that. So Ka is equals to the negatively charged ion times hydrogen, just like comes from this reaction, divided by the neutral, the one that did not dissociate. Parenthesis denotes the activity. In dilute solutions, molar concentrations are applicable. What does that mean? That means if you have very dilute solution, remember when we talked about gamma, which is the single ion activity calculations, if you have the solutions very dilute, then the concentrations are almost equal to the activity. That's what it means. The molar concentrations are applicable. We can use them instead of calculating, which is a very tedious process to calculate the activities. So you can substitute the concentrations for activity in this particular case if you have dilute solutions. Okay, we rearrange the above one. You remember, you know about cross multiplication. You bring this hydrogen down and these will stay on top of each other. So Ka over H, cross multiplication, this is over 1, remember. So H times this, okay, still times this when you have cross multiplication, equals this. So Ka over hydrogen equals the negative ion over the molecule. Keep in mind, this is extremely important. We'll go back and forth, and most of our next coming discussion will concentrate in this, and keep this in mind. Ka over hydrogen equals the activity of the negatively charged ion over the neutral or the molecule. Okay, so dissociation of a carboxyl group, again, the expression indicates that the concentrations of the protonated and deprotonated forms of the organic acid will be equal. This will equal this when the hydrogen ion concentration of the solution is equal to the acid dissociation constant. If we go back, remember this ratio. If this equals to this, that means this equals to this. So when Ka equals hydrogen, the concentration of these two will be equal. So when the hydrogen ion concentration of the solution is equal to the acid dissociation constant, Ka equals hydrogen ion concentration or activity, or when pKa equals pH. Remember, P denotes the negative common logarithm of Ka or H. When we say small p, it's the negative log of anything. In chemistry, if you write small p in front of anything, that indicates its negative logarithm. So that's where pH comes from. Minus log the hydrogen activity in solution. So pKa minus log Ka, the same thing. So then remember this important characteristic. So when Ka equals hydrogen or pKa equals pH, the concentration of these two will be equal. So this will be 50% dissociated, 50% neutral molecule. For the given dissociation reaction that we talked about, the methoxyacetic acid, Ka, this is from the literature, 2.9 times 10 to the minus 4, and pK, if you take the negative log of this, of course, you change this to 10 to the number. Instead of 2.9 times 10, it'll be 10 to the certain number. Okay, and then you take minus log, so it'll be the positive of that number. Okay, so it will be pKa equals 3.54. You can do this through your calculator, or you know how to change this from this form to the log form, and then you end up with just this particular number, pKa equals 3.54. So remember, we go back to the information we have just said. When the pH, because remember, Ka, when pKa equals pH, that means when Ka equals H, that means the concentration of the two will be equal. So we go back to the same statement. When the pH of a dilute solution containing the methoxyacetic acid is 3.54, if the pH of that solution 3.54, the concentration of this, the neutral ion, and this will be equal. Same, we've been saying the same. So think, if we were asked at what pH the concentration of the neutral and dissociated molecule and the negatively charged ion will be equal at the pH which is equals to the pKa of that compound. When the solution pH is less than the pKa, remember, going back again to that ratio, remember the Ka over hydrogen that we have seen before. When the solution pH is less than the pKa, remember, pH negative log. So if this negative log is less than this, that means the H itself will be more. The negative log is smaller, that means the log larger or the number is larger. So when the pH, when the solution pH is less than the pKa, the ratio of Ka over hydrogen will be less than 1 because hydrogen will be greater. So this ratio will be less than 1. And then again, you go back to the original equation. As the negative logarithm, this is just what I have been saying, it's written here, as the negative logarithm of a parameter decreases, the actual value of the parameter itself increases. So if you take a solution of pH 2 has 10 times the proton concentration of a solution with a pH of 3. So the lower the negative log, the higher the hydrogen itself, and of course, the higher the concentration of that solution. So pH 2, which is smaller pH number, which is minus the log of hydrogen ion, has 10 times, sorry, 10 times the proton concentration of a solution with a pH of 3, 0.01 molar versus 0.001 molar. Therefore, the concentration of the undissociated acid, with a 0, we put 0 so that it shows the neutral molecule, will be greater than that of the dissociated acid CH3 or CH2 or minus, the negatively charged ion. If you keep in mind just back and forth, go back to the original K and how we derive the ratio of K over H and the ratio of the two entities we have, you can follow all this logic easily. Just keep in mind, you don't have to memorize these things because these things you can always derive them from the equation that you have. When the solution pH is greater than the pKa, when the solution pH is greater than the pKa, the ratio Ka over H will be greater than 1, and the concentration of the dissociated acid will be greater than that of the undissociated. Easily, just keep up with all these ratios with the original. Now, this is how it changes. In this diagram, we have the example we talked about, the methoxyacetic acid with pKa 3.45, and then we have another methoxyphenol with the pKa 9.65 as a function of solution pH. So as you change the pH, you can change the ratio of the ion to the whole neutral molecule. So if you look for the one we were interested in, we talked about, this is it. Okay, so at very low pH, like look at this arrow, it shows the concentration of the ion. And this one, the concentration of the molecule. So, of course, as one decreases, the other one has to increase because the concentration of the original is the same. It comes from the same source. So, when are they equal? Remember, when the pH of the solution is the same as pKa, pKa 3.5, that's where the two graphs meet. When they meet, that means they meet this value and the value of this are equal. So they have equal value, which is 3.45. For the other one, because the pKa is 9.65, they will be equal at this point, 9.65 pH, 9.65. So if you can look at them easily, you can see which one changes, which one decreases as the pH increases. And of course, the other one will increase opposite to it. And when this one is maximum, this one is minimum naturally. So it all makes sense and very simple. Okay, we talked about the acidity. Now we talk about the basicity of the organic functional groups. Basicity of organic functional groups may also be described by pKa values similar to that of acidic groups. We will see how. We'll take example. Pyridinium ion dissociates as follows. Remember, we started with the ion, pyridinium ion. It gives you the neutral molecule, plus it releases hydrogen. Here it looks like it's an acid. It gives you hydrogen. We will see how that's not the case. With a pKa 5.2, dissociation of the ammonium ion of the amino acid glycine is as follows. Okay, this is the amino acid glycine. Again, this is the ionic form, and it gives you the neutral. It releases hydrogen. Basicity of the N moiety. N moiety, this is the N moiety, the part that contains the nitrogen. That's what we call it moiety. This section, the part that contains the nitrogen. So the basicity of the N moiety on these two compounds is not readily apparent from the above reaction. It appears that both protonated pyridine N and amino groups are acidic if we look at them in these particular equations. The basicity of these functional groups is illustrated as follows. Now, if we take the neutral molecule in water, it takes up hydrogen. This is how it became ionic, takes away, and then it gives you hydroxide ions. And the other one, the same, the glycine, same way, takes away from water a hydrogen, it becomes NH3 plus, and of course, the hydrogen left the water, so it releases the hydroxide ions. At equilibrium, the distribution of the pyridine and amino functional groups between the protonated and deprotonated forms is described by a basicity constant. We call it Kb, since they are bases, so we will call that Kb. We take the pyridine reaction as an example. Okay, this is pyridine and water, remember. It took hydrogen and it released OH from water. Again, we write the equation. Sorry. In this case, remember, pure water, its activity is 1, so it does not appear in the equation. All the rest of them have to appear, but not water. Okay, water will be here, so we do not have since it's 1. Sorry. The pKb value provides a measure of base strength, just as the pKa provides a measure of acid strength. Remember, these organic bases and acids, they're not strong acids and bases, so they dissociate to some degree depending on their pKb or pKa. Basic compounds that have pKb, remember B, not the A. Sorry, between 0 and 14 are called weak bases. The closer the pKb value is to 0, the stronger is the base. So the smaller the value here between 0 and 14, the stronger the base will be. Because remember, these are all weak acids and bases, but we compare them to each other, some of them stronger than others. How can we compare them based on their pKb? The pKa and pKb values for any given compound are related. Remember, at the beginning we said pKa, and then we talked about pKb. How do we relate them together or with each other? Values for any given compound are related. One can be computed if the other is known. We will see how. Simple. For the pyridinium and ion dissociating reaction that we just saw earlier, we wrote it in Ka fashion. Remember, the protonated one gives you the molecule plus hydrogen. This is a Ka, okay? So you take hydrogen times this divided by this. The concentrations of the proton and the hydroxide ion are related through the dissociation of water. We know when we have aqueous systems, always dissociation of water is what controls the pH of that system. So the hydrogen plus OH, water dissociation to hydrogen plus hydroxide ions at equilibrium Kw, that W of water, equals activity of hydrogen times the activity of the hydroxide, and that way hydrogen will be Kw over H. So we have the value of H in terms of OH and Kw. And of course, we can do the other way. We can find the value of OH in terms of Kw and H. Kw equals 10 to the minus 14. I think all of you know that. pKw equals 14 at standard temperature 25 degrees Celsius and pressure 1 atmosphere. Substituting the value of hydrogen into Ka, so Ka that we just have derived, we put instead of hydrogen Kw over OH. And then Kw, remember, we can have cross multiplication and then reverse them, so that the Kw will be above. Kw over Ka equals the negative over the positive. The right side of this equation is equal to Kb. Then Kw over Ka equals Kb, or P, take the negative logs of all of them. Negative log of the ratio, remember, this minus log of this equals log of this, and then you rearrange. pKw minus pKa equals pKb. The pKb value for the pyridinium is 14 minus 5.2 equals 8.8. And pKb for glycine amino group is 14 minus 9.78 equal 4.22. Therefore, remember we said the closer the pKb to 0, it will be stronger. Therefore, glycine has pKb 4.22, okay? The other one had pKb of 8.8, so the glycine is a stronger base and protonates at a higher pH or lower pH than does pyridine. That finishes these, and I will try to put those slides for you in some form in Dropbox later.